la caméra ajoutée, le son. Ouais. Non, je sais. Parce que ils ont dit une thermale de ah ouais, il y a que sur cette partie. Vous allez gérer avec ce temps. Ben, en fait, vu que le lien, il est. Le lien, je ne peux pas. Ouais, si tu veux. Ouais, mais ça, tu peux enlever. Parce que s'il est coupé là. Il n'y a personne. Si, ben. Oui, c'est clair. Je peux lui envoyer. Je l'ai envoyé. C'est pas notre projet. C'est qui va.
Je l'ai envoyé, mais elle m'a pas répondu. Hein? Je l'ai envoyé, mais j'ai pas eu de réponse. Après, si elle est en cours. Ah, te l'as envoyé? Oui.
Tu lui as dit le lien YouTube de l'arrêter. Tu lui as dit de la YouTube en sort. Non, je ne sais pas. Tu lui demandes hein? Je t'envoie le ça.
J'ai dû vous l'envoyer.
C'est pas mal,
hein? Ah, attends.
Ah, c'est parfait.
Hello.
Hi.
Fine. Can you hear us?
Yes.
And can you see the screen?
Yes, I can.
Okay. So.
Okay, good.
Okay. So hello everyone, and thank you for being there today.
Just
For my-
I will present
Okay.
the committee. So it's an honor for me to preside this committee. I will present the member. And first, reviewer, Mr. Alexandre Alahi, professor at EPFL Switzerland. Vincent Le Petit, second reviewer, professor at ENPC Paris. Fatma Güne Mohamed, assistant professor at Koç University Istanbul. And your supervisor, Mr. Eljoua Zablouki, researcher at Valeo, and Mathieu Koch, professor at Sorbonne University, and myself, Catherine Achard, professor at Sorbonne University. And you can.
Thank you. So thank you again, everyone, for being there today for my PhD defense about efficient representations for autonomous driving. So, as it was said, it was directed by Mathieu Koch at Sorbonne University, and it was also supervised by Eljoua Zablouki and Alexandre Busch, and in the past, Michael Chen from Valeo.ai. So, to understand what happened in the last 50 years since the first prototypes of autonomous vehicles. So in the 80s, as you can see, there is the emergency of having autonomous vehicles that can drive on the road. And now in 2024, we have some kind of robotaxis that can drive in some roads in San Francisco or in other countries. And the major difference is the different types of sensors that we have now compared to what they have in the past. And the sensor will lead to all the data that is gathered, and also all to the AI model that will be trained on this data. So we will see how it has changed the field. So the question about the sensor, the main one is how many sensors do we want to have, and also what kind of sensors do we want to have. So we basically have two different categories. The first one is the perception sensors. The idea is to be able to understand where we are in the environment and to understand the different agents and also the roads and all the elements. And the other category is just the localization sensors that will give you information about your current state, where you are in the world, and also your current speed, your current braking angle, etc. So in the first category, you can find the LiDAR, that is kind of a light of a radar, and also a radar and cameras for helping to have an understanding of the scene. And for the localization, you have the well-known GPS and EMU that give you information about your states and your speed. And as you can see on the right, so you have many different configurations for where to put the different sensors and how many of them. But one thing that we can say between the different actors of the field is that all of them use cameras. And you will see in a moment why cameras are really useful. And we will put our thesis in the multi-view camera settings. But you can also see that other actors use different other kinds, such as radar and LiDAR, in combination with the cameras. So the fact that we have to understand is why multi-view cameras are good for autonomous driving and why they are useful and why they are used. And so we will compare this field versus the LiDAR field that basically use a LiDAR to get some 3D point clouds. And the main difference between the two is that LiDAR provides a common reference frame, meaning that if you use 2D multi-view cameras around your scene, you are not able to gather all the information and to have some coherence between the views. It's not given in a straight manner, while the LiDAR gives you a surrounding views, a surrounding information about your environment. However, the LiDAR is like really expensive compared to multi-view cameras, so you have two distinct fields in the community. The one using this efficient but expensive sensor that will lead to LiDAR plus multi-view camera systems, and the other field that use only multi-view cameras, but that can bring some less costly autonomous vehicles. So once you get all the data with your sensor, the idea is how are we able to given this data have the kind of output that we want to have. So the question is, what are the typical outputs that we want to get for achieving autonomous driving, especially the perception part. So the perception part is about how you will understand your environment and the correlations between your agents and the road and everything. And this is a typical pipeline that you can find in most of the multi-view camera systems. So as you can see on the left, you have the sensor that gather data at every step, so at a high frequency, because the cameras give you high frequency information. And then each camera, you extract information that is called features or latent representation, given a visual extractor for each camera. So the first one is processed by one extractor, the second one by another, etc. Once you have your 2D information, since your final goal is to have a 3D information, we need to project the 2D information into 3D, and it will be done through the projector. And we will see later what are the different kinds of projection that we can have. And in order to gather the information and to make them more coherent in the AI model, we will use a processor that can be either convolutional or attention-based. And as you can see, the choice of the representation is really different from what we have as the input. So the idea is that maybe the 2D images is not the good reference frame that we want to have in order to gather the 3D information around us. So we will talk about one another that is that was really common a few years ago, that is a bird eye view, that is typical flattened representation of all your environment. And the last one is basically a 3D voxels, so cubic representation. So this is a 3D representation that is more costly and more heavy, but that it gives you fine-grained details on your information. And above the outputs, you can see that you may want either to detect the objects, so giving some bounding boxes around them, or to get a 3D reconstruction that is basically kind of semantic segmentation of all the cubes, or finally to get a bird-eye view segmentation of the vehicles. So the blue rectangles represent the vehicle, but in the top-down representation. So to see where are the different papers in the pipeline, so we will work on this common pipeline, but then we first talk about the point bed, that is a paper that is a new architecture for 2D bird-eye view segmentation, and we will see how it has changed some paradigms. Then we will talk about Ghost Render, that is a new plug-and-play module that can be branched to every 3D occupancy model, so the kind of architecture that works with these 3D voxels that output the 3D voxels segmentation. And then we will talk about Jafar and NAV, two new feature upsamplers that deal with the feature extractor. So the feature extractor is the first component of this pipeline that allows you to extract meaningful representation from your data and sensors. So as I said, we will talk about three different topics in this thesis. The first one will be focused on 2D bird-eye view segmentations, and I will talk about the point bed that was published a few years ago. Then we will talk about 3D occupancy through a Ghost Render, and finally about the feature of sampling with Jafar and NAF that we presented jointly in the last chapter. So let's start with the 2D bird-eye view segmentation with this paper, point bed. So 2D bird-eye view segmentation, the situation is the following. We have multi-view cameras around our car. So basically, we want to have a 360 representation and of the different views around us. You can have like small overlaps between two cameras, but that won't change anything in this field. And the idea is, instead of having the RGB images as a reference frame, we want to have the bird-eye view reference frame. So you have to imagine a kind of a bird or someone looking down around you. So you have like the ego vehicle that is in the middle of your square, and every square corresponds to one column in the 3D space. So compared to the image, you have a common reference frame. So meaning that if you look at the two images, they are not representing in the same space, while the two images can bring you information at different cells, but in the same reference frame. However, you are losing some granularity compared to RGB images that can be really of high resolution. And the task more specifically is the following. So we still have our images captured by the sensors. So there are fixed images. This one is a front camera, and this one is the backward camera. And the final objective is to have this kind of segmentation where blue rectangles represent a vehicle, an agent, or so it can be a car, but it can also be a pedestrian or lane segmentation, whatever you want to segment. And in this field, you have also a small subtlety about what we consider as visible cars and as occluded cars in the ground truth, meaning that a car is occluded if it's not fully visible in the RGB space. So it's different from fully visible car because you have to complete a little bit what you see to understand that there is a car behind an object. And as you can see, the main challenge will be how we will move from this reference frame that is representing the camera, one camera reference frame, to this common one. So you have 6 reference frames, 1 per camera, and then we want to have only one with the axis, where the axes are different. The pipeline is the following. We will follow what is the paper called a simple bed. So simple bed propose a kind of a projection that is different from what was done before, and also how to process the information. So compared to, for instance, a performer, you don't have like any attention at all in this pipeline. You have only 2D convolutions. And also the projection is not a deformable attention, but it is what we call the bilinear grid sampling. So let's dive into this pipeline. You recognize most of the components of the pipeline I presented before, except that these parts where basically you have 2D information, 2D features, 2D latent representations that are extracted through a visual encoder, but you want to project this information into 3D. So what you basically do, you basically, given the coordinate in 3D, and given the camera parameters, so the intrinsic and the extrinsic parameters, you are reprojecting this point into this image, and then you are linearly interpolating the features given the coordinates of the projected points. So you are doing this one per camera. So you have like 6 big volumes that you will gather the information that you will flatten. So basically a sum or a mean over the features in order to have your final bird eye view. So this bird eye view contains information. For instance, this cell contains information of this pillar, but also this one and this one. And then in order to have some coherence in this representation, you are basically performing 2D convolution neural networks on top of it. And then you have a final head that gives you the segmented agents, car or pedestrian or whatever you want. So the main challenges in what I presented before is like you have 6 different big volumes, one per camera projected. So this is the memory bottleneck of your approach, especially if you want to have a fine granularity. So since you are constructing a cube, you have like a cubic complexity, and also you are using it per camera. So if you have like now 12 camera, you need to build 12 different 3D features. And also another drawback of this approach is that it doesn't focus where it matters. So what does it mean? So imagine you want to perform vehicle segmentation just to know where are the different vehicles that you see in your camera. And imagine that you know, or at least you have inferred that you have a building on the right and on the left because you are moving in a city. So you might not want to lose computation and time to inspect if there is a car inside the building. First, because you can't see what is inside, and secondly, because it's not probable that there is such element inside of it. So the idea is, are we able not to waste our time and compute in this kind of region, but more focus on the road or on some prior that we have about the current scene. And so this leads to Point Bev. So Point Bev was a paper I was presenting in a conference about segmenting the bird eye view using a sparse approach. So let me explain you what does it mean. So consider that you are able to know where are the different regions of interest. So you are able to know if you have some prior that there is a building or that there is a forest where you don't want to waste some compute. So instead of considering the whole dense map, you will only consider some cells representing the regions that you want to query. And the question is, if you have such knowledge, how are you able to process the different queries? So you recognize the input that are basically the images. But first, instead of projecting one camera into one global, one unique 3D voxels, you will reproject the cameras into a common one. And so to achieve this, you need to record some parts of the linear interpolation in order to have a parallelizable interpolation that will reproject the points not into one camera, but in all the cameras in a parallel manner, and also that will gather all the information and reduce it using, for instance, a summation. So this step means that you are not projecting one image into one 3D voxel, but you are projecting all the images into a single one. And then you are like flattening the 3D representation into a 2D one. And the question is, can we better process this representation? So instead of doing 2D convolutions, we will move to what is called sub-manifold or sparse convolutions. And the idea is that for each point that you want to have to upgrade the features, so that's basically centered on the moving window, you will compute the convolution between this point and all the points that are activated in this kernel, so in the window surrounding the point, and you will only perform the computation on this activated point and all the others that falls into the window. That allows to avoid wasting compute on some unuseful regions and to avoid using, for instance, dense convolutions with zero padding. And then the rest is nearly the same to output the final predictions. So about the task, we are still able to perform different kinds of segmentations, as the vehicle, pedestrian, or lane ones. And the ground truths are basically 3D bounding boxes given by a LiDAR that are rasterized and segmented in bird view. So, but one question remains is how are we able to sample the points? So I've said that if we know where to look, we are able, with the previous pipeline, to infer the estimation. But where do we know where to look? So we proceed with the two steps. The first one will be to have some knowledge about the region of interest. So imagine you sample like points randomly or really with a coarse pattern. You just want to infer if this point might be interesting or not. And you will build some, so you perform one prediction, and then you will build some anchors that will be the region of interest where you will basically densify the signal in order to perform another prediction, so the fine path, to get the final signal. And in practice, what does it mean? It means that if you have a regularly coarse pattern where one point represents one query, in the coarse path you are able to randomly select, to regularly select points, and then you will densify the signal around the point that you are considering to be relevant. And you can see like there is a high correlations about all predictions and also the overlay the ground truth, meaning that we are able to sample only where it matters, avoiding spending many different compute on uninteresting regions. Qualitatively, we can see that you have the ground truth in the middle and the prediction on the right. So we are quite good about reconstructing the predictions. If you see blurry effect, it's just the confidence level of the presence of the car. And you can also see that there is a strong correlation about the different masking regions and the ground truth and the prediction, meaning that we are indeed able to segment interesting regions. As you can see on the bottom, it can also be the case for smaller objects such as pedestrians, and it can also be adapted for larger objects such as lane estimation or drivable area. Quantitatively, this method, since it is a sparse, we move from a dense approach to a sparse one, so we are able to gain many memory and also many frame FPS compared to the previous methods. So you recognize simple lens that was presented at the beginning. So we can see that we can lower the number of points while keeping the same score. So the score is basically the IOU. And also in terms of quantitative evaluation, we have evaluated on for 3 different segmentation tasks on 2 different image resolution and 2 modes, so with and without visibility. And we have seen that we basically have a better score than the previous state of the art at this time. So that shows that it leads to strong results. And this one is for pedestrian, and the 2 others are for vehicle segmentation. So just before to move to another topic, we might be interested in how to leverage temporal information. So I have presented many videos, but I've not talked about a video pipeline. So let's see how can we do. So what was done in the past was called the zero padding. So you are basically only using the information that was overlapping your present reference frame in blue with the one in the previous time steps in yellow. But you will zero pad the regions that are not overlapping. So you are not able to use information from a really long time steps. But alternatively, what can be done is that you will build the points around you for your present time, but then you will reproject the different points in your past representation. How to do it in detail? So you will consider a sub-manifold temporal attention across a query point. So you have a query point that is basically your current cell that you want to infer and you want to transfer past information. You will consider a spatial temporal window, and you will perform an attention between this point and all the points that fall inside this spatial temporal window. And doing that, you are able to process videos and to output video. And for instance, when you use 8 frames on benchmark for vehicle segmentations, you are still having some gains, even compared to the model I presented before that was better than the others at that time. So now we have talked about 2D segmentation, and we will talk now about 3D occupancy. So the task is highly correlated, but a little bit different to the one I presented, and it leads to a Ghost Render paper that was published. So the 3D occupancy task is the following. Since we are in multi-view camera setting, we still have as input the multi-view cameras. But when we think about what is actually doing the bird eye view, so the bird eye view is actually compressing all the information in a pillar, meaning that imagine a situation where you want to have information about the drivable area in purple, but also about the car and also about the tree. You don't exactly know if at this cell, so at the bottom, you will gather information only about the tree, or if it will mix information about the tree, about the car, and also about the drivable area. So in some cases, such as the one I presented, you want to have more higher granularity about your understanding of the scene in order to avoid having such confusing situations. So you want to reintroduce the vertical reasoning, but you will lose some efficiency since you are working with 3D voxels instead of 2D cells. And when you look at the different pipelines, so basically this is the 3D voxel that you want to get into segments. But since this is a heavy representation, so cubic ones compared to the quadratic one, different methods such as TP deformer or student occupancy use different kinds of representations. So some are more efficient, such as the triplet approach. Some are more heavy, such as the multi-scale voxel approach that leads to strong baseline. And they basically optimize this pipeline. So you have the images, you are extracting one representation per image, you are projecting this representation into an intermediate representation, that can be, for instance, triplet, and then you are processing the different intermediate representations, converting it to 3D voxels in order to get the final 3D occupancy. So here is just a 3D rendering of the 3D voxels. So you can see as one cube is representing one segmentation in 3D, but from a point of view. But when you look in details at how they are basically trained, they are basically optimized during a one-by-one comparison. So on the top, you have the ground truth obtained by the LiDAR, and you have a prediction on the bottom using, for instance, TP deformer. But the loss is basically a cross entropy or a Lovász loss or a dice loss, whatever. But what it does, so it basically compares these predictions to this one. So you are not doing like neighborhood covariance or localized covariance. You are just trying to know if this voxels corresponds to this one. And this also means that you are treating the voxels in the same weights. But in practice, the voxels are not equally important, and you might not want to have such equal weight. So considering the front camera, where you have some pedestrians in the blue circle, on the bird eye view rasterized projection, you have like red squares here. But in such cases, you don't want like to put the same weight for the pedestrians, so for these small rectangles, to, for instance, a wall that you are not even able to see. So here you don't see what's happening on the left, even with the front left camera. But in your ground truth, because they are accumulating multiple LiDAR point clouds, you have some information. So you have two different kinds of tasks. The first one is to reconstruct what you see and to segment it. And the other one is a little bit to complete what you don't see. But you don't want to have the same weights, especially like doing a wrong prediction on an object that is close to you can lead to really bad behavior of your car. So you want to be at least really confident in what you see. So in order to do this, that means that we need to reproject the representation into a point of view and to heavily penalize this reprojection. But we need to find a way to do it in a differentiable manner and also efficiently during the training. So the solution provided is called the Ghost Render. So this is a plug-and-play approach, meaning that you can use it for different models for any model that is present, for instance, the triplet, the TP deformer, or student occupancy. You still have the 3D losses comparing one by one the voxels, but also you have another loss that is a rasterized loss, a rendering one. And the idea is the following. So you want to be differentiable, so you can use Gaussian splatting. And you also want to be covariant, meaning that you can't, for instance, voxelite the ground truth and project the voxels, but doing another thing for the predictions. So in our cases, we decide to consider the voxels, convert it into simple spheres, and then to project the spheres using an algorithm that is called Gaussian splatting in order to obtain two different views. The first one is the depth estimation that gives you information about where is the current location of the first visible objects, and also this semantic segmentation given this camera. So please note that this camera is not constrained to be the one of the RGB sensor. It can be whatever you want because we are projecting the final 3D voxels and not from the RGB locations. So the task, as I said, is 3D semantic segmentations, and the controls are 3D semantic segmented voxels obtained from the LiDAR, so the sensor that we are not using as input. And the losses are a combination of the 3D losses that I presented, and also the render depth estimation and semantic segmentation. So in terms of qualitative results, so you can see some videos about what are different sensors, but also some reprojection of your voxels. So because you can't clearly imagine what are the 3D representation, we are reprojecting it in RGB, in the location of the RGB sensors, but also, for instance, in the top-down representation. And here I put the contours. But more interestingly is how can we improve the current models. And we have performed we have plugged the methods in several methods, such as TPD former and the one I presented before. So we have used 3 datasets for 3 models. And we have also focused on the MIOU, that is the standard metric, and another one that is called the Ray IOU, that takes into account the fact that you want to be really precise in the first visible objects in order to avoid having some collision with pedestrians, for instance. And you can see that we improve the previous methods using only this additional loss during training. And also we can wonder what is the efficiency of our methods when we don't have the 3D losses, so the one-by-one comparison, but we only consider the 2D loss. And compared to previous methods, such as the render occupancy that we are using NERF, so neural field rendering, we obtained a better performance. So before to talk about another subject, one interesting question is that I've said that we are not constrained to put the cameras in the reference frame of the RGB sensor. The question is, do we have a strategy to put the cameras to render different views of the scene? And in fact, indeed we have. So basically, when you project in your RGB camera, you are not having information in behind the occlusions, behind the object that you can't see. So the idea will be to elevate the camera a little bit in order to constrain this kind of voxels. And also we will have the top-down representation in order to be sure that we will have access to all the kind of occluded regions. And you may wonder if it has an impact on the final scores, and the answer is yes. So if you have a fully random strategy, you basically have, you don't have like really good scores. So randomly, meaning that you will put the increasing randomly in the scene, but you keep the increasing parameters as the one of the RGB image. So it's like realistic cameras, but put anywhere in the scene. But if you use, for instance, the sensor, so you have improvements, but using like the elevation, allowing us to have some optimization about what you can see, you have some gains, and also like moving a little bit the camera backward and forward allows you to have the better scores. So the elevated plus backward forward movement was the strategy we have used to obtain our previous results. So now we will talk about the feature of sampling with 2 different papers, Jafar and Naf. So they are doing almost the same thing, so and sharing many ideas in common. So that's why we present them jointly. So I've talked many times about the feature extractor, the vision extractor, and the way to have a latent and to process the RGB images from the sensor. And in the previous pipelines I've presented, like the vision extractor is trained. So basically, during the optimization, you are updating the weights of the vision extractor to obtain the features. And this is a classical vision encoder, where the encoder is trained per task. But one drawback of this representation is basically we are reducing spatially the features. So if you have, for instance, a high definition image, the output will be only middle or low definition features. So you are losing the spatial representation in order to have more knowledge in the depth in the channel axis. But another kind of vision encoder are called vision foundation models. So the idea is to train once the model for many different kinds of tasks, for instance, for performing a semantic segmentation, depth estimation, open vocabulary, or whatever. But instead of training it then per task, you will only fine-tune or add some probings on top of it in order to obtain the different tasks that you want to cover. So I will represent the vision foundation model with a little with this logo. But the vision foundation models and also the classic vision encoders, as I said, they are compressing the spatial resolution. So if you have this representation height and width here, you are lowering the two in order that you have access to more information. So here you can see like the PCA projection of each features. But if you are clearly able to distinguish some motorbikes on this image, or for instance, a small tiny car that is really far away in a different image, you are not able anymore to see them in this PCA of the features. But the idea is that instead of compressing the representation, can we at least keep the same representation, so keep the same resolution, in order to better see, for instance, you can recognize the moving motorbikes that is there, or the other objects of the scene in a better way. So the challenges are the following. We want to find a way to upsample the representations for any tasks. So for performing semantic segmentation, depth estimation, or gradient activations, or whatever you want to cover. But we also want to focus on outputting any resolution. So depending on your task, you may want to just to multiply by 2 the spatial resolution of your features, or to multiply by 8 or by 16, or maybe sometimes even higher than your input signal. And the answer was this pipeline called Java. So Java is trained for one vision foundation models, and it relies on 2 mechanisms. The first one is an interaction mechanism, and the second one is the global attention. So it's an attention-based method. The attention will allow you to transfer the spatial shape of the query, and I will explain how I obtain the query, to get the final spatial resolutions. And also, it allows you to make interact the features extracted for the VFM to the features extracted from the image. So we are training an image encoder in order to learn the weights we have to apply for one vision foundation model to reweight the low resolution features in order to get the high resolution ones. But as you can see, the interaction mechanism is a way to infer and to put some knowledge of the low resolution representation of our current VFM into the key that will be used in the interaction between the query and the key. So the key have some knowledge about what are the current representation, like semantic meaning or more broad knowledge compared to only a pixel. So because basically the image encoder is has a really small receptive field, so we are really localized information. And the task is an unsupervised feature sampling, meaning that it can be used for any kind of task. And the ground truths are high resolution features obtained with high resolution images. When you look at the PCA of your final features, so this is, for instance, for DynoV2 with register moving bus. So this is the low resolution features, the one you are obtaining just putting the image or the video into DynoV2. And this is the final PCA of the upsampled high resolution features. As you can see, you have like a sharp boundaries, and you can better distinguish the different elements of the input. And also, due to the attention mechanism, we are able to adapt the shape of the query in order to have different output resolution up to 8 or 16 until we reach the out-of-memory boundary. But we have some remaining questions. The first one is a pragmatic one. So this approach was training one upsampler per vision foundation models. So many different vision foundation models exist. Some are more better for some specific tasks. For instance, a clip is really used for open vocabulary, while DynoV2 are more focused, or DynoV3 on depth estimation, segmentic segmentation. And so the idea is, are we able to have one upsampler, so to merge all the upsamplers into one, to perform upsampling for any kind of vision foundation models. And also, when we looked at the attention maps, in the architecture, Jafar used a global attention mechanism, meaning that it's a plain attention. However, when you look at the attention maps, we recognize that the interpolation is a local phenomena. So the question is, can we do better than performing global attention? And can we, like for instance, use a better mechanism to only focus where it finally matters? So as I said, this is what we want to have. We want to, for any kind of images, for any visual foundation model, so DynoV3, CAPI, or CLIP, we want to use only a single upsampler, so a way to learn how to rewrite the features of the low resolution in order to get the high resolution features for any task, semantic segmentation, depth estimation, open vocabulary, or whatever. And also, since we have observed that our mechanism is a global one, but the attention map are really sometimes localized, we want to have a local attention, so an attention that is more focused on some neighborhood of our current point of interest. For instance, if you want to upsample this point, you will only consider the blue rectangle as the keys instead of considering the whole map. And this led to this architecture, NAF, Neighborhood Attention Filtering. So at first glance, it is really close to what was presented in Jafar. But as you can see, there is one missing block that is the interaction mechanism. And also the global attention now is a local attention mechanism relying on neighborhood attention. So to train such pipeline, we will fix or use multiple vision foundation model, but we can use a single one during the training in order to get the low resolution features. And then we will try to learn how to reweight the features without having any kind of interaction, because if you have an interaction, most of the times it means that you are relying on some hyperparameters of your vision foundation models, for instance, the number of channels, so you can't like generalize. And having this kind of approach and having this form has allowed us to link with the Fourier theory and to see that we are actually learning the discrete transform of the kernel aggregation weights. And this leads to a method that are able to upsample so low resolution features from any kind of vision foundation models. And the task is the same, like we are performing unsupervised feature upsampling. The ground truths are still low resolution, high resolution features, and we are still using a simple MSE loss. Qualitatively, we compare, for instance, the interpolation of bilinear interpolation, that is a really well-known algorithm that allows from a mathematical principle, to Jafar and to neighborhood attention filtering. And as you can see, like in some cases, like Jafar tried to mix the low resolution features into a single one. So this might be due to the fact that sometimes the low resolution features are not the best possible ones, and are indeed, since they are reducing the spatial information, mixing and having like a lower quality, while the neighborhood attention filtering is able to better keep the semantic of the different pixels. And we can also see other visualization in the thesis, such as depth estimation, PCA, and open vocabulary. So in terms of quantitative results, if you are just looking at efficiency, since we have moved from a global attention mechanism to a local one, so when we compare to Jafar and also to one concurrent work, NEUP, that was just published, we are able to perform 3 times faster inference, so 3 times faster upsampling. But quantitatively, we did like many different experiments on like almost 300 combination of data sets for 5 tasks, so simple ones such as linear probing for semantic segmentation, desestimation, but also open vocabulary more complex ones, such as video label propagation, on the 15 vision foundation models, so with multiple sizes for different families, etc. And we have seen that in all the evaluated case, we obtain strong results and like most of the times the best results compared to the other methods for any kind of task, and also compare like to 6 at least to 6 baselines, such as the simple one, linear interpolation, or the more modern one, such as FitUp or Jaffa, and also AnyUp. You can find more details in the thesis. So the Fourier theory that was subtly taught during this presentation allows us to have some analogy also with the filtering theory. So we are not only providing an upsampler, but also a filter. This is due to the form of our current pipeline. But this means that we are also able to perform different kind of computer vision tasks, such as denoising. So the task is the following, and we basically keep the same architecture that was designed for feature upsampling, but we will train for image denoising and see that it works. So we have different kind of noise, so Gaussian noise or salt and pepper, for different level of attack. And we see that when trained, the clean images, the noisy images are denoised into a consistent image compared to the ground truth. And also, in order to link with the model view pipeline I presented before, we have basically evaluated an upsampling of the low resolution features branched into the point bev or simple bev pipelines. So I've talked in the first part of the presentation, and we have seen that using, for instance, Jaffa leads to better score than without other FitUp or even linear interpolation, meaning that it can be used in more complex pipelines compared to only linear probing, and that leads to interesting results. So the summary of the contributions are the following. So in the first part, we have talked about 2D border view segmentations, and I've proposed an approach that is a sparse approach, focusing only where it matters, and that allows you to have efficient in terms of memory and speed. Then we talked about video occupancy, a plug-and-play module that is branched to many different architecture, and that leads to 2D to 3D consistency, so avoiding like to collide a pedestrian. And then we have talked about how to enhance the feature of the visual extractor, and that led to 2 different papers. The one is a VFM specific, while the other one is VFM agnostic, and it works for any resolution as output. And since we are working on a vision foundation model, it was designed to work for many different tasks, and also many different vision encoder. So to go a little bit further, about the feature upsampling, what can be really interesting is that when you look at the vision foundation models, how they are trained, like recently, but most of the vision foundation models are not scale invariant, meaning that they are training their vision foundation models for a specific image resolution. But when during inference you want to use either a lower one or a higher resolution image, you are having like really low and noisy features. So some really recent papers propose to have some kind of scale invariance, but I think it can be further studied. So it was work done, for instance, with radio or DynoV3. But also on the driving part, so we have seen the emergence of autonomous driving foundation models. So the first approach was basically to use the vision language models that was kind of able to understand the word and how they are linked with the different text, but then to adapt it to autonomous driving specifically. And we have switched to word models, but I think like many works still need to be done in order to have one autonomous driving model that can be used in many different tasks. that will focus on efficiency, so time inference, and also to have geometry awareness, a fine-grained geometry awareness of your 3D scene. So the list of the contributions are the following. So PointBev was done at Valeo.ai with also Florent and Bartuccioni. GoStender was done at Valeo AI. Jafar was a collaboration with Paul Guéron, and also NAF was a collaboration with Paul Guéron at Sorbonne University. And below you can see like 2 different collaborations from Valeo.ai. And I will thank like my advisor Alexandre Gilloise Aloki and also Michael Chen in the past, and my director Mathieu Paul. Thank you for attention.
Okay, thank you for your presentation. So we will start the question session with Alexandre Hall.
The first of now. Oh, okay. Yes. Thank you. Thank you for an amazing presentation and fantastic work and outstanding outcome and all the awards. Very impressive. It's really important. I don't know from where to start, but I will start from most recent to coming years from lab and Jaffa. So here, when you train, it's actually feature agnostic, right? So lab is independent to the feature. It's across all the potential features, right?
Yes.
And so when you do training, do you train across multiple features, or will you only train in one and generalize for?
So for the training, so we have tested many different configurations. So the question is, during training, so during inference, we are able to infer to different kinds of vision foundation models, but during training, we need to find a recipe. And the recipe, the best one was to use the Dino V3 features. And why Dino V3? Is that because we are performing a 2 steps training, right? The second steps, we are using higher resolution images and higher resolution features, so even higher than during the first step. And since the Dino V3 is kind of a scaling variant up to some point, we are able to have a better consistency. So during training, since you are comparing high resolution features to low resolution features, you need to have a kind of consistency between the output of the vision foundation models, and Dino V3 was one allowing it. But we are testing with multiple backbones, for instance, using a combination of Dino V3, Rajo, Dino V2 with register, etc., that it led to lower results.
I see. So there is one optimal VFM to use for training that will generate what is what you're saying.
What I say is that the quality of the vision foundation features during training have an impact on the inference quality. Yeah.
But you have not trained with multiple of them jointly.
Yeah, yes, we have tried the multi-backbone training. So during, for instance, you consider 5 or 10 or 20 different vision foundation models. During one step of the optimization, you are optimizing, giving this vision foundation model, and you are switching between the different steps. But it led finally to lower features. But because, for instance, if you are using a clip that was not designed for having a consistency between high and low resolution features, it will have like a noisy impact on the gradients and low to lower. To have a lower quality of the reweights of the low resolution features. Like even using Dino V3 during inference to have clip, it's even better to use Dino V3 during training than to use clip, even if you have a consistency between your inference and your training.
And during training, you have never used the VFM for clip.
So we have did some experiments on many of them, and the clip was also studied.
Thank you. I guess maybe if you wanted to go back, you will, so maybe still on this line of work, cost, so you shared some computational cost, like potentially this can run at almost real time, right? You said 20 frames per second for the upsampling.
I can check it was this kind of
The order of
disorder. Yes.
I see. But you still need to run the VFM, and then you will take the VFM output. You still need the image, and then I mean this is something that we have to add, right?
Yeah, so this is something that you can add, so it will depend of the impact it has on your final results. So if you are thinking just, for instance, the topic I discussed at the end, to train a vision foundation models, so it doesn't have an impact during inference, because you can, for instance, imagine that you have a distillation mechanism where only the teacher has this kind of sampling, but during training, the student will basically just perform a simple inference. But yeah, you're right, it has an impact on the total cost, so memory and also frame rate. And you have to study if it's worth or not to use it in your pipeline.
See, so I was supposing that it's still very useful, but did you do this study or not? There are use cases where it's better to directly go higher. So.
Can you repeat?
But indeed, so you have the alternative that your VFM or your main model is outputting the high resolution, or it's outputting the low resolution, and you have your upsampling instead. So, but is there a use case where the classic method is faster?
So basically, this corresponds to the large image baseline. So if you want to have high resolution features for like the current vision foundation model, you need to use a larger image as input. So it has a really high impact on the inference time. So like the order of magnitude is basically another one that the upsampler, because most of the VFM are quadratic based, quadratic complexity, and also like the quality are worse. So there are some tables in the thesis where you've seen that not always, but in many tasks, using a really high resolution image will have a negative impact on your final metric.
So it's a no-brainer to use your upsampling with all the pipelines of it.
I will say that it's might be interesting to consider using it. So we have studied many different tasks and combinations, but I won't say that it's 100% working. On all these experiments that I've done, it was working. So I think it's worth to try.
So now if we go back to your Gaussian rendering, so here, have you also looked at the foldable Gaussians to solve this problem?
So we have, so the rendering is a static rendering. So we don't have like a temporal version of this approach. Like, I mean, we could like, what I wanted to say that the approach that I presented are basically static ones, but in practice that we could have like aggregated multiple time steps to do the predictions. But at that time, it was, we wanted to find a way to update the quality of the static models and to see if it works. And but I agree that it can be adapted to deformable Gaussians and to temporal ones.
And then more philosophical questions about all this line of work and like what is the best representation at the end, 3D representation of for autonomous driving the application. Do you still believe that voxel or Gaussian are the way to go?
So
the perception.
okay, because I was about to observe for in the general setting, but for the perception pipeline, I mean, if you want to have efficiency in your pipeline, like the multi-scale voxels are really heavy, and also like the symphony strategy with the voxels plus query. So, for instance, the bottom part symphony led to the better score, but maybe also because it was a more recent papers. I'm not truly convinced that one representation is better than another intrinsically. I see that when I look in the history, every 3 years the best representation change. And so, however, I will tell that if you want efficiency, you still need to find some way to optimize in a clever way the representation.
But this old 3D object detector, where does it stand? I mean, compared to, because here, I mean, it seems to be quite costly for every voxel to have a custom trophy. Whereas the old school object detection, it's just one boundary box and maybe the depth, and you might have the same information.
So if you are commenting about the task in itself, I think that the task it has appeared when Tesla promotes some video about how they are doing their own protocol for autonomous driving, and you were able to see like a 3D kind of representation. And I think that's one reason that we have this kind of community working on 3D occupancy. It might be interesting to know if like a rasterized 3D detection, to compare at least with rasterized 3D detection. And from my point, I mean, from what I've studied in the 2D perception, so I've compared 3D object detections, rasterized in Bordelu versus 2D Bordelu segmentations, and the 2D Bordelu segmentation directly led to the better score. But maybe it depends on the quality of the last detection models.
I see. And but so there's all this also pipeline that occupancy is not good enough, you know, for perception. For instance, for humans, you don't want to just put a cuboid of voxels for them. You want to understand their orientation. You want to understand maybe their skeleton. You might want to understand where they look. So where does it come from?
In this task, you don't have this kind of information.
So then we need to run another perception step to augment this.
So it depends. If you want like to work on 3D occupancy segmentation, but in a temporal model, the temporal model will need implicitly to infer and to understand how the scene is evolving. So we are not having as the output, for instance, the 6 pose estimation of the pedestrian. But since you want to do forecasting of 3D occupancy, the model need to understand how the scene evolves.
Super. Thank you.
You're welcome.
Okay, should I ask any questions? Okay, so thanks a lot for the presentation today. So I think it was very easy to follow. The manuscript itself was also super clear, so that's also always enjoyable. And congratulations for all the papers. It was a very impressive palmarès. So congratulations for the new CVPR. It was not accepted at the time when I read the manuscript. So I will ask questions in the reverse order of Alexandre. So basically, it was maybe the first question for point Bev. I was expecting the motivation for the method to be faster, but I'm not sure it's already faster. So that you have less processing. But or is the motivation just about memory? But memory is not necessarily super critical. So was the motivation also to be better? I'm not sure I saw anything about the speed in the manuscript, but maybe I missed it.
So, like, I mean, it is faster, so I'm quite surprised that this was not in the final manuscript. So, but honestly, it is faster, but it depends on the spatial image resolution that you have. So, in order to achieve like a faster model, you need to find what is the bottleneck of your model, and so the answer is that it depends of the cost of the processing of the images compared to the cost of the processing of your intermediate or final representation. But if you are like doing in this community, people work at middle resolution, and it leads to faster results compared to simple web and Performer.
Because it's not necessarily, so the sparse convolution can be a little bit, or can be slower than just a brute force convolution. Directly you intermediate, so basically the curve, okay, so that's your intermediate representation. So it depends on the resolution of this.
Yeah, and also how they optimize, how the library has optimized some manifold convolutions compared to the other ones.
Exactly.
Especially like on the new GPU, like you are able to do some like the kernel itself has some knowledge about the sparsity, so the things are evolving a lot. But at that time, it leads to convincing results about the FPS.
Okay, got you. Okay, so you confirm that it was faster. Maybe so it's really each single time step at a time, so you have no temporal consistency or whatever it is in this world.
What do you mean by
So that's so for example for the masks. So yeah, so the mask there is probably a very strong correlation between the mask at time t and the mask at time t+1.
Yes.
Maybe you could you save some computation by trying to propagate the mask, or that's not necessarily completely clear?
So
How do you do that?
yeah, indeed, we didn't have such strategies in the model I proposed. So the question is really interesting because it's really correlated to like the overlapping regions, because when you have two different masks for two different time steps, you are basically having some knowledge on what is overlapping, and you can consider that the cars are moving a little bit, so you can have like a region of interest around your previous segmenting mask. But also you still need to put some queries on the new undiscovered areas. So it was not done, but it is feasible and interesting.
So yeah, so the new parts you could process them systematically.
Yeah, but also you can process them as I presented in a regular pattern, but also if you have other priors such as HD maps or LiDAR, you can only sample the points that are given by the HD maps or the LiDAR in order to avoid sampling all the regions.
Interesting. So for the next method, so for Ghost Render, it sounds already a brute force method to do the rendering, to, at least to me. So for me, it works because it's some sort of multitask learning, and when you have multiple objectives, basically you get more data. Somehow you get more training data, and does it work because of that, or is it because of some other reasons, or maybe can you imagine another task which would be easier than rendering your voxels?
So about the first part of the question about the justification of Gaussian splatting. So at the beginning of this project, you have tried many different ways to process the ground truth, for instance, doing mesh rendering or just voxel rendering. But what was a little bit tricky that we wanted to do the same rendering for the predictions. Otherwise, we will have like a difference between the processed voxel. So imagine you have a voxel that is rendered on the ground truth. So you will basically see a cube, but we didn't have access to easy library for performing in a differentiable voxel rendering. So the first idea was to use voxel rendering in the ground truth on CPU, and then during training we use the Gaussian splatting while we are using multiple Gaussians in order to mimic the cube. But then we have a discrepancy about how we process the ground truth versus the predictions. So we needed to find a way to use the same. So we finally switched to Gaussian splatting because it is easily differentiable. So I'm not saying that mesh rendering, for instance, isn't, but it, like from what I've seen, it required more. The compute was heavier and also slowing down the pipeline. And also about the multitask question. So I think I agree with you that most of the benefits come from the fact that you are adding some losses in a new kind of task. So the two tasks I presented were the natural one coming from the 3D segmentation, since we only have access to segmented objects, and also if a point is also because like we have a class for the void, so we can have like a depth estimation using or not this point. I don't see easy all the task, but if you have another knowledge about the detection, it can be performing detection in the 2D images. But in this case, the ground truth won't be only 3D segmenting voxels, but also 2D or 3D bounding boxes.
I was thinking about simply counting the voxels of each class and compare the number of voxels in the prediction and in the bound truth. That would be super simple, but that would also be a new task which is still related to what you have.
Okay.
I'm not claiming that it would work, but that would be worth trying.
Yeah, I agree that we can do, for instance, a histogram of the different class and comparing the different histograms. But in this case, so we are not doing one-by-one comparison, but we are doing a set-by-set comparisons. But using this rendering approach, what we wanted to achieve is that we have a consistency on some neighborhood and some spatial regions. And that might not work with the set-by-set comparison.
Okay.
And also, this approach tries to solve the case of the pedestrian that is really close to us and that will be heavily penalized by the depth estimation. Because if you are, imagine you have a voxel that is really close to you, the depth will be really bad. And so this is penalizing this situation.
Yes, so you give more importance naturally to the voxels that are close to the canal.
Yeah.
Or to the canal in general.
And that's why it leads to really good improvements on the RAI-IOU metric. That is basically an IOU, but that takes into account the depth of your first visible object.
Okay, so that makes sense. Good. Okay, just two more questions. And one for each method. So if I understand correctly, so Jafar is trying for one specific resolution or one specific output resolution for can you I was a little bit confused. So that's because you mentioned multiple resolutions as outputs. Just
Okay, so no, it is trained at a multiple resolution, and during inference it can be used at multiple resolution. So during training, what you can do is basically to have a varying. So the shape of the final input is the shape of the query because of the attention mechanism. But during training, you can use as a high resolution image. For instance, you are multiplying the natural image by a factor of 2, but it can also be a factor varying between 2 and 6. So we'll have like natively multiple resolution during training. But what also works is just to have a ×2 high resolution image, giving a ×2 high resolution features. And during training, because of the attention mechanism, but also an element that is not present here, that is a rope, that allows you to interpolate the positional embedding to a higher resolution. You are able to query to have a ×16 image, even if you are trained on ×2. But I think in the paper it was trained on multiple, on a varying range. We have tested different strategies and it leads to the better score.
But it's because you train it for multiple resolutions explicitly.
Even if you are, so the naive case is to train for a ×2 resolution. So you are giving, for instance, 1000 by 1000 image to get the high resolution features. And you are also feeding a 500 by 500 image to get the low resolution features. And you are trying to learn the ×2. And if you are doing this, you are still able to extrapolate to higher resolution ratio. But alternatively, you can having varying ratio during training, but both leads to close score. But the final strategy was having this kind of varying ratio.
Okay. And so maybe one final question, which is not necessarily the policy. Are you familiar with, so about NAF, are you familiar with not local means?
Yes, I am.
Because it sounds very, very similar at the end. So what you do, or I think what you do is better because it's there is some learning involved, but I think it's very, very, very similar. In fact, so you just the output is the weighted sum of the local vectors.
Yeah. However, if I remember correctly, non-local means by definition are non-local, where in our case we are only focusing on neighborhood region. So maybe in non-local means you can query points that are far from.
Non-local was relative. It's just depends on the size of your neighborhood. But non-local means you look into a region or patch that. So, for example, if you consider one patch, so it's still a region. It's just that it's not a region of 3 by 3, but maybe far. I mean, I'm confident that your method is still better because you have more computation and more learning into for the weights. So in non-local means the weights are directly computed from the correlations between the patches. But the attention between the keys and the correlates is probably very, very similar to the correlation scores that was used in non-local means.
Yeah, probably I agree, but also more broadly, all the interpolation community only focus on the closed region. For instance, linear interpolation or bicubic ones are only considering the 4 or 8 neighborhoods. But yeah, it's also the case for non-local means. But so I see it's not in the manuscript, but we have tested a non-local means for the denoising algorithm, and it leads to a really bad scores compared to the deep learning methods.
Okay.
And we have also tested DM3D, something like that, for denoising the classical denoising algorithm when you know in advance the attack of a Gaussian noise.
Okay, so that's this one I know. So is that the bilateral filter?
No. I think it's D3D, BM3D, anything like that.
Okay. So I will stop here. Congratulations again for all these papers and the presentation. Thanks.
So, Katla, can you hear us?
Yes, can you hear me?
The floor for your questions.
Yes, I can go ahead. Thank you very much for this great talk. My first question, like the point pair model, it is very good at, it's great that it can handle both like pedestrians and cars, and this is very impressive, right? Like I was curious about this very small out of distribution objects which we don't have labels for. Do you see any hope that like we will be able to represent, I don't know, some chicken on the road, and we will have the corresponding, bird's eye view representation of that on the map? What do you think about this kind of hard to label rare classes, representing them in bird's eye view?
So maybe I wasn't really clear, but we have indeed access to the 3D bounding boxes of the pedestrians in the same way that we have collected the 3D bounding boxes for the cars.
Yeah.
So like when we train for the pedestrians, we are rasterizing the 3D bounding boxes that was given by a 3D detector on the LiDAR point clouds. So we are not totally
I know. This is more like an open-ended question. Like, is there any hope? Like, what do you see we need to do? Like, what is the next step to handle such cases?
So if I understand the question correctly, is that what is the next step to be able to segment unknown objects during training? And one solution could be at least to link the final representation with open vocabulary ones, and to be able to have the correlation between the extracted features and the feature of the class of our vocabulary in order to be able to segment during inference different kind of objects. But it was not done in this committee, or at least I don't know such papers doing this. But we can basically plug an open vocabulary model doing some click losses to have any kind of class during inference.
I guess in that sense, for example, 3D occupancy is more preferable, right? Like if you compare the two in terms of this, like you don't need labels for occupancy, right?
So you can use this kind of approach in the 3D occupancy methods, but you can still do in the 2D border view. So once you have I mean, if you are doing open vocabulary and you have a depth estimation, you can like reproject your final prediction either in bird eye view or in 3D. And in such a way, I think you will be able to train to infer a model to segment the objects. But maybe the 3D case is more suited.
Okay. About the second part, I was curious, like you have this additional rendering loss, right? What can it achieve that you cannot do with the voxels, like the voxel losses? What does it bring additionally?
So basically, since we are having gone through from the 3D voxels, we are not adding new information, but we are treating the information in a different approach. So as I said, how the model are optimized, they are optimized by one comparison. And so when you look at the predictions, you are putting the same ways to know if a wall that is not visible is correctly predicted than a pedestrian that is clearly visible. So what it brings first is a different reweighting and penalization of your predictions, especially on the visible objects due to the depth estimation. So if both leads to the same global extrema, but using this one, you are leading to a more realistic extrema. Or the reverse.
Okay. And about the last part, when we learn upsampling, like, can you hear me? So how do we know if we recover or hallucinate information? Because it's not like image upsampling, right? Like we are learning to upsample features. So how do we know we are not hallucinating but recovering the details of the initial image?
So you're right, especially when you're trying for specific vision foundation models. So for instance, Java, you are heavily having a correlation between the quality of the reconstruction and the quality of the low resolution features. For instance, if you have like really noisy or bad representation of your low resolution objects, you are not, so it's not a generative approach, so we are not able to correct the wrong features or the noisy ones. We are only able to reweight them a little bit. So if your inputs are noisy, you won't be able to have like a really sharp and clear final outputs. But you can have a reweighting that is better than just upsampling the final the initial low resolution. However, it's not necessarily the case, or at least it's a little bit different for NAFT, where you learn the reweighting independently of the low resolution features. And this can explain, this is one option why you are not mixing a lot the different pixels. So if you are using a vision foundation model that has a low quality, or that is good but not the best quality, you can propagate in Java the weights of the badly semantically and global information during your final output, where it's not the case in NAFT. But I mean, it still depends on the quality of the features at some point, since we are doing relating and we are not generating new features. But one other option could be to be able to understand what is the current distribution of your features and to try to correct it during inference, having the same kind of distribution, but you are still relying on your initial distribution.
Maybe one last question is more like a hypothetical what if question, like if the LiDAR was free, like what would be the percentage of your thesis that is still, you know, relevant? If LiDAR was freely available, scalable.
So let's take the paper one by one. I mean, if you have LiDAR, focusing on region of interest is still an important problematic instead of considering the whole 3D representation. So like, it will really switch the way you are dealing with the perception pipeline. So if indeed you are considering 3D point clouds, you basically have directly the prior about where to look and where to sample. However, the LiDAR is imperfect by essence, so you really might still want to focus around the regions of your initial LiDAR point clouds as it was done in the fine pass. So that can be at least interesting to extend the receptive field of your initial point cloud. For the Gaussian rendering, since it is something that is if it is a rendering, you can still, for instance, convert the point clouds into some Gaussians and to reproject them, and you will have like another multitask loss. So you by essence, the point clouds constrain the depth estimation, but it can be another way to have a densified signal for the depth estimation. It can be interesting, and since it doesn't lead to more cost during inference, it's worth to try. And for the feature sampling, if you consider that you are using a LiDAR with the vision method, it can be still used for the vision encoder. If you are totally removing the vision extractor, you can't use such pipelines. But for the vision encoder pipeline, you can still want to upsample during your final pipeline the features by a factor of 2 or factor of 4 and see what's happening. But in this case, I consider that you are training everything end-to-end, and it might lead to different behaviors where we have only studied the vision translation paradigm. So we are only upsampling the feature of a frozen representation.
Okay, thanks.
You're welcome.
Thank you. So I have also some questions. First, the segmentation, the first contribution. I'm not sure to understand how fast you onshore at the beginning in your results. How have you done? You sample the first point.
So to sample the first point, it depends of what you have access. If you have access to anything, you can just regularly subsample the initial grid. So if you have a 200 by 200 grid, you can take 1 point over 5.
On your results, how have you done?
So once you have your...
The table.
Sorry?
In your results, how
Yes.
have you done? Remember?
So in my results, most of the results are done using this subsampling pattern, except for the LiDAR results. And the LiDAR results was done performing this approach, but considering the LiDAR point cloud during the course pass. So during the course pass, we are only taking into account the points of the LiDAR, and during the fine pass, we are focusing on.
In fact, my question was, can we learn how to pass the first point?
In a deformable way?
Yeah. Can we predict this first something in an optimal way?
Yeah, so I've tried such approach where you try to either learn the offset from the regular pattern or to directly, for instance, have some queries attending all the image, and then you have an NLP on top of the queries to give you a certain number of anchor points. So that is totally feasible, but in practice, it leads to lower score. But you can imagine, for instance, a LARA pipeline when you have tokens that attends all the images, and then you have an MLP over the tokens predicting 100 sampling points, and then you are focusing around them. But to achieve the best results, you need a kind of pattern.
Okay. And for in each function, you sample all the points in the lightning group.
Yes.
And it is possible to predict, so using, for example, reinforcement learning, but when to look factor, in order to know to sample for all points.
Yeah, I think if you can have like a kind of so it is feasible in the sense that you might have a reward meaning that you are actually on the car in order to avoid sampling points that are not. So you can have a really high neighborhood, but only a few points that are really interesting. So in your way, if you want to do a reinforcement learning, we need to define a reward. It can be basically a binary reward. And then to predict the points, it can be an MLP on the final features to assert, to guess the offset. So I didn't try, but I think it can be done, at least theoretically.
Okay. Do you think it could improve result or go faster?
I think if you want to have maybe more gains in this community, reinforcement learning might be a way, but you have faster things to train and to develop that can lead to better. I mean, reinforcement learning needs to introduce many different things in the actual pipeline that can be, since nobody, at least up to my knowledge, have tried such implementation, you will need many times to know how it will behave. Whereas you can use a more modern approach and basically just changes some components and see if you have more natural improvements.
Okay. Now for the second contribution, can you go on slide 26, please? 26.
Oh, pardon. Sorry.
Oh, it is not this one. It is this one. We agree on in the last figure, but the black points are the camera.
Yes, the 3D locations of the camera.
Because it seems to me that we have more cameras in the one on the right than on the left. Is true or not?
So you have basically 6 cameras. One.
6 on the last figure.
So the last figure is where you put a random. So the location of the camera is randomly in the whole space.
But more camera or not?
No. So I think the plots are done, for instance, for 100 cameras. But since in the sensors you are always using the same location, you are always sampling at the same points. And as you can see, in the elevated plus around, you have the same number. Or if you are counting, you have the same number.
And have you studied the number of cameras? If this number has a great importance on the results.
So what we have done is basically one dynamic camera per step. So we have, in every step, we have the bird eye view to have access to points that are not visible, but also one additional camera from this elevated plus around approach. But we have also tested in the case that we have multiple, but since basically basically it leads to the same scores, but we have to consider that at each time the camera location change. Like the gradient for 6 times one different camera versus one gradient for 6 camera aggregated is almost the same, and leads to that's why it leads to the same score.
Okay, another question for features of something. Can you go to slide 35, please? Yeah, the task is feature something. The one proof is higher resolution features.
Yes.
We use NMS.
Yes.
So why is it unsupervised? If you use NMS with
Okay, so it was unsupervised in the sense that regarding the task that will be performed after.
yeah, but this task is totally supervised. Your task.
Yeah, so basically all the vision foundation models give you an output, and we are supervising on this output, but we are not considering that we are supervising on the final output of the target that we want to upsample. But it was unsupervised in that sense, but we can be more specific.
And another question is, are we really to make this something? Can we not use lower resolution features to directly predict the final at a higher resolution without this?
I mean, theoretically, it can be done, but this requires to change the vision foundation models. Because if you want to have directly the output in a higher resolution, it means that the vision foundation model or backbone, the output is the high resolution. But we consider in this case that whatever, like you have a whole community on having the best vision foundation model. They disagree on many things, but that's why and also like for the standard backbones, like all the backbone I know are basically reducing the spatial resolution. I don't see any reason why it's not possible, except that for computing reason, at least during an intermediate step, you need to reduce a little bit the resolution. But yeah, I mean, in the end, they all have a low resolution.
I agree that we can use the full information is inside this low resolution feature. Because if they are not here, we cannot predict.
Yeah.
So why don't we use directly this lower resolution features to directly predict the final task without something?
Okay. So if you don't have like this branch, like the image encoding branch, and just given the low resolution features, trying to learn the weights. So the first point is that it will be really hard to have a learnable protocol that works for any kind of vision foundation models, because you are basically learning for a specific distribution what will be the upsampling. And also, what is really interesting here is that so you don't exactly know how the vision foundation model was trained, and it is really probable that it has learned some information on the high frequency due to how it extracts patch representations. And so this branch is a way to re-put in the final reweighting the high frequencies of your RGB image. Because basically you can say that, for instance, the VFM leads to a totally noisy low resolution features, like random noise. That's not totally true, but I mean, they are not perfect. And they are losing some information about your input.
And do you think that if you learn something in a supervised way, according to the final task, perhaps that the weight will be different?
Yeah, I mean, the weight might be really different, especially because the tasks are naturally different, but
On the final results, or they will be better or not, you think?
I think if you train a specialized model for a specialized task, it will be slightly better.
Yeah. Okay, and so what is the goal to make this something diagnostic?
But the question also is available for why are we training vision foundation models compared to train one vision encoder per task? And the question is just that we want to have more flexibility, and we also see that we can benefit from the different tasks where the exhibition foundation model is has big knowledge compared to the others, and that can benefit from it.
Okay, good.
Thank you.
Okay, thank you. So, I will give the floor to your supervisor now, and first, Éloi Zabloquet.
Thank you. So I don't really have questions, but just I want to congratulate you for the very impressive work. You have been really the one proposing really the core ideas of all your works. Your works they cover diverse topics, which is well never trivial to change topics. It means new literature, new baselines, new metrics, and so on. And so you were able to do that really in a very efficient and easy way. For it. At least it looked easy when you did so. So congrats for this. Also, I mean, we all know the field is very competitive, and you often have the right idea at the right time, and sometimes having the bad surprise of other works that came just a few weeks or months before a deadline. So you also always found a way to pivot, to rebrand the ideas, to never drop your work. So congrats also for this aspect of the work. I'd like to stress also the huge experimental work. You were very always very at ease with all the details of the protocols. Sometimes having really fair comparisons to previous literature is not always super easy, and that's something you were really keen on doing well, and which makes in the end good science, which is reproducible and that other people can work on. So congrats also for this. Yeah, in the end, it's four very nice contributions as leading author, plus two nice collaborations also. And I'd like to mention your four main contributions that were accepted at the first shot, which is really not always the case. And so congrats also for this.
Yes.
Yeah, so that's it. I enjoyed a lot of working with you. Thanks, Loïck, and congrats again.
Thank you very much.
Okay, thank you. Thank you very much for your presentation today. It was fantastic. I mean, I really appreciate what you explained and the way that you explained your work today. I would like also to thank to all the jury members. In particular, I mean, we were very pleased to have you in the room, Alex. And thank you very much for coming. And that next time, for sure, next time we will be able to jump in between your different teaching period. But okay, thank you so much to find a way. I mean, like to be here with us in video and to participate to this jury. Thank you very much. So yeah, it was great. Also, of course, Vincent, to have you also in the room. I mean, like even if you are not so far in terms of lab, but at the end of the day, I mean, like if you live in Bordeaux, it's still an experience to come. In particular, at that time with the French weather. And of course, Catherine also. Catherine moved very far from this place. Okay, thank you. So, as I said, I mean, like, thank you. I mean, like, just to give a little bit of context, and I think, Alex, you mentioned that it's 3 years. You're perfectly right. I mean, like, we are exactly on time with this PhD. So, it's great. I mean, like, why? Because I mean, like, I think tomorrow you have like 1 week off just to finish the value time of exactly 3 years. You know, and so it's fantastic, and it's great to be able to be on time. It's not it's never easy. I mean, like to finish. And I would say that your PhD had really, I mean, like went in a smooth way. I mean, like all the time. I think you. Smooth in the term of typically, I mean, like to be able to publish your first work after 1 year, and then your second work after 2 years, and a year and a half or something like that. But to have really, I mean, like step by step, the second big paper and the third one, and let's say cherry on the cake. I mean, just having like the CVPR accepted this weekend. So I don't know if you had that in time when you when we decided, I mean, like to do the defense today, that the result of CBPR would have been like during this weekend. Okay, okay, this is perfectly timed. And so, I mean, like, it says something about, I would say, mostly also about the maturity that you really, I mean, like, improve during your PhD, and it's also very, for a supervisor, I mean, like, this is really, I mean, like, something that's, it's crazy, I mean, like, when we get, I mean, like, you get, I mean, like, in terms of idea, in terms of originality, in terms of quality of the work, and the type of let's say, work that you can build on. And I mean, typically, I mean, like in terms of autonomy for that, I mean, step by step, from the first one to the second one and to the third one, I would say that also implementation of the idea. So what I call the execution was already, I mean, like time after time, and always more impressive. I mean, the way that you implement, evaluate and validate all the different approach. And this is just to say, I mean, like how many tables we have in the NAF, just to say that it's completely crazy, and we are not even able, I mean, like, to discuss about some of them because there are too many. And also about the writing and the way that you present, I think really, I mean, like it's step year after year, I mean, you become really, I mean, like more and more clever about that. And it's so, I mean, very pleasant for a supervisor, as I said. Also, it was really, I mean, like all the time very easy to work with you. I mean, like you are really a good guy, a nice colleague, and I think as well, I mean, like on the value side, on the university side, you were able to work with different people on different projects, and we can see here, I mean, like let's say when we yes, Paul and Luis, for instance, on the university side, and as you we say with Laurent typically, and of course your co-supervisor Michael, Edouard, or Alexandre, I mean, on the other side. So this is also, I mean, like yes, interesting. I mean, like to see that for you, I mean, like it was yes, very easy, and like kind of open mind to be able to do, I mean, like with so many projects with so many people. You also, I mean, like I think as Edouard mentioned, I mean, like you also did some work that has not been presented today, but that was very useful in different contexts from the end of your internship, and after, typically for Lara, for instance, you did a lot of experiments also, you tested many things that give you also, I mean, like some of the idea that you can after, I mean, like find a way, I mean, like to use in the different present project that we mentioned here. I would like just, yes, to mention also, I mean, like all the things about, for the last project, we were thinking a lot of things about the attention, flash attention, sparse attention, many things like that. We expected to find a way, I mean, like to do something, and finally it comes with something of the feature. So it's fantastic, and I would like to finish on that because it's really, I mean, like from the NERIPS to the CVPR, I mean, like it's not the end of that story. I think you will really open different things, and in a very interesting way, I mean, like for computer vision people, is that even after this kind of deep learning things, and like we can also, I mean, reconsider some kind of old problem of something, let's say, in a different way. I mean, like why using this kind of deep learning things, and this is always interesting to say. I mean, like deep learning is not always, I mean, the end of the story. I mean, and there are still, I mean, like some problem or some question that can be, of course, reconsidered thanks to this kind of tool. So thank you for that. You mentioned Fourier transform, by different things, and I think also all the things about the non-local means that have been mentioned also by Vincent are somehow one method that we really can reconsider and to see what's going on. Okay, so thank you very much for all of that. It was a pleasure to have you for 3 years.
Thank you, Monsieur.
Thank you. Oh, this is the end. We stay here? Yeah.
Okay, so yeah, I think we stay here. So yeah. Et je trouve que ouais, vas-y. Mais je vous laisse le zoom alors. Je vous laisse parce que on reste avec toi. Ok. Et là, on fait.
Madam, my colleague medical imaging.
J'admets. Okay. Maintenant, we stay here on the Zoom. We stay here, the jury. We talk together. We discussing something is going to go to the end of the last. Memorize, I mean, like the defense today, and then after, I mean, all the people come back. We just read the draft, okay, and after it's over. It's okay for you?
Sure.
Partage.
Ouais.
Je vais vous donner.
Ah, tu veux couper le partage? Ok, ouais. On va faire ça, ouais.
Non, ça suffit.
J'ai pas arrêté le partage, je crois. J'ai arrêté le partage.
Je pense que
Je vois moi.
on peut pas pousser les murs, hein, par exemple.
Arrêtez le partage, excuse-moi. Voilà, c'est bon. Et il faut que tu s'ils ont partagé, tu peux donner une gestion. Alors, qu'est-ce que
C'est bon, tu peux faire un truc?
Ça y est.
Ok.
Merci.
Juste, attends, j'ai pas viré le zoom. Attends.
Il faut garder le zoom.
Le YouTube.
Ah oui.
Ouais, ben.
Ouais,
Ah, voilà.